Okay, so I guess last week we talked about statistical learning and back learnability, and we talked about the two versions of that, one under an assumption of realizability and one without it, which we called agnostic back learning. And we saw a few examples of learnability. We saw that finite classes were always learnable, and then on the homework you saw that you worked out an example of an infinite class that was also learnable. So I guess today we'll look at the sort of limits and classification of learnability. So yeah, we're still going to work in this special case of just looking at classification. It's just the simplest interesting case, and we'll take the last function to be the risk throughout today. And then yeah, an interesting theorem that we look into is the no free lunch theorem. So this is a sort of negative result in that it kind of captures some limits of learnability. So it says that if, let's say, alpha is a learning algorithm, and we're assuming that the domain is large, it's bigger equal than 2m, where m is going to be the number of samples that we look at. Then in this situation, the theorem says that there exists a distribution D over x cross y, such that basically it's a realizable distribution. So the loss under D of f is equal to 0 for some f. But alpha does poorly on this distribution. So if the probability, if we sample from this D m samples, the probability that the loss of our learning algorithm on that sample is bigger or equal to 1/8. This is at least 1/7. So it's basically saying there's a high probability of having a high error for the learning algorithm.
When we compute the loss, we take the average mistake, right?
It's it's the probability of
between 0 and 1, right? Yeah.
Yeah, so it's the risk, which is so LD is the probability that if we sample XY from the distribution, then h of x is not equal to y. So I guess an immediate corollary of this theorem is that if x is infinite, and h is the hypothesis class of all functions, then this h is not backlearnable. Right, because in that case, for any m, we have that the size of x is large enough, and by this theorem, we cannot have the kind of epsilon delta bound on the loss because of the theorem. Does this make sense? Any questions so far?
Yeah.
All right, so I wrote down basically a complete proof in the notes of this theorem. And I think that was a request to kind of focus more on the kind of high level ideas, which I agree with. So basically, we'll try to understand why this is true. And basically, so maybe the first step is going to be we're going to turn this statement on the probabilities into a statement on the expectation. So the first idea is that if you have the expectation of some variable, let's call it phi, if this is bigger or equal than 1/4 for phi between 0 and 1, then this implies that the probability that phi is bigger or equal to 1/8 is bigger or equal to 1/7. So this, why is this true? Well, if this probability of being bigger or equal to 1/8 was less than 1/7, then we get the expectation. So this is always bounded above by the probability that phi is less than 1/8 times 1/8 plus the probability that phi is bigger or equal to 1/8 times, and we assume it's at most 1, so it's times 1. So in this case, if this probability is less than 1/7, then we get something that would be less than 6/7 times 1/8 plus 1/7, which I think is 1/4. So that's where the 1/8 and 1/7 comes from.
And
So
in
this allows us
principle, we could have chosen like an infinitely many different pairs for epsilon and delta to make this work.
Yeah, I guess 1/8 and 1/7 is just sort of
They somehow feel nice.
tightest, or like, well, you know, they're kind of a nice pair that works well.
Yep.
But, yeah, all we really care about is something positive for both of them.
Isn't it a proof in the other direction though? Didn't you show that the probability satisfying this implies that?
Well, I showed that if the probability is bigger than 1/7, then the expected value is
It's
less
not.
than 1/4. So.
Yeah, right.
So we're going to focus on this claim, which in this particular instance is going to be, so we want that the expected value when sampling from m samples of the loss of alpha s is bigger. So now I guess we need to choose a D which satisfies the first condition. So a natural thing to do is to just fix an F, to take an F from C to Y for some.
I think X at this point,
Well,
right? Or
I want it to be defined on
okay.
some subset C, which has size 2m, which then we can define a distribution kind of corresponding to this function. So it's a distribution over x cross y, and it's we can take it to be basically a uniform distribution across C, and then the y component is just given by f. So one way to write it is that it's an average over C over points that lie in inside of C of a delta distribution at x and f of x. So what this is doing is just takes this finite subset C, looks at the, so this is a subset inside of X, looks at the value of F, and this is the Y direction, and takes the distribution, which is a uniform distribution across C, and the Y component just has the function. Does this make sense? So now for such a D sub f, we automatically have that the loss of f according to that distribution is 0. So by construction, it's realizable. So basically, what we want to prove is that there exists some f from C to Y such that the expected loss of the learning algorithm when you sample from this df this is a bigger equal to 1/4. Yeah. So far we reduced it to this claim. And then now the idea to prove this, so we're basically trying to show that there exists such an f. And then what we're going to prove is that if you pick an f randomly, uniformly randomly from all of the functions, then this property still holds. So that in particular implies that this inequality holds for at least one such f. So yes, we can say that the maximum over such f's of the expected loss. Just register it in. It's going to be bigger than the average overall all such f's. So it will be enough to show that this average is bigger or equal than 1/4. Does that make sense? Okay, so, but then now, I guess one benefit of doing this is that this expected value itself is an average, and then we can basically switch the order of the two averages. So basically, we can say that this is the same as the expected value across samples. Oh, should be a little more careful. Maybe I'll keep it a little sloppy. There's an expected value of a kind of a sample from C to the M. So if we just sample the X component of the averages over F of the loss. And now we can say that this is bigger or equal than the minimum across all samples. Of this average. So basically, if you can show that for any sample we take from any sample of M points from C, if we can show that this average across all functions is bigger or equal than 1/4, then we're still ready to prove this claim. Does this still make sense? Okay. So I guess now we're left with wanting to show that for any it says for in C to the M, we have and I already said it. So the average over all functions f going from C to Y of the loss under this sample. So that is just spell is for no alpha as for
Isn't it lost with respect to DF?
It's the sample
Uh,
loss. Empirical loss on the sample.
yes. So yeah, I guess yeah. Yeah. So this is the because now we switched to expected values, so we're looking at a fixed sample and the loss over that one. So maybe this should also say this bar here.
What does this mean? What does LS bar mean?
Yeah, okay. So maybe I should put that. So yeah, maybe because basically if we have an S bar here in CM, we can define the corresponding sample in X cross Y to the M, which is just applying F to this sample, right?
Yeah.
So if this is like SI, then this is gonna be like SI comma F of SI.
And this isn't a distribution though, right?
Yeah, this is a sample.
Okay, but alpha also gets S bar F, right?
Yes, right. Yeah, it should have been written as part.
But isn't this value always 0? Because it's
Well, we don't know what alpha does. Or what
Um,
alpha learns.
okay.
So yeah, alpha is a fixed learning algorithm. So it just returns some function for each sample here. But yeah, that is important that these samples do depend on F.
But can't I choose alpha which given S bar F, well, we can compute F from that, and then it will return DF, or not DF, it will return F.
Yeah,
can
so for any specific F, there could be such an alpha.
Oh, but we have only half.
So the claim here is that if we average over all of F, then for any fixed alpha, this is always going to be at least 1/4.
But I think I can choose an alpha which always has 0.
Have we said that C has twice as many points as M? Yep. Because that was a key
Yeah,
part of the proof.
Oh, so here.
Yeah,
So the domain of
assuming
the
so.
function has twice as many data points as you
Okay.
can observe.
Okay. That clarifies that. Okay.
Yeah, so it is definitely important. So we're assuming the sample misses a certain number of points from C. But yeah, I think you're actually right. This should still be DF. Like we want to look at the average loss across all of C, not just a specific sample. Maybe. Right, and then we can actually write this out explicitly as because we know what DF is. So this is like 1 over size of C as the sum of the indicator function that alpha on the sample. This is sum over X in C at X is not equal to F of X. Right. So, does this make sense now?
Mhm.
Yeah, sorry, you were right. This needs to be d sub f for the loss. Okay, so basically what we're trying to prove here is that if we average over all functions, then on average we still have a relatively high loss. And then, so what's the idea for showing this? Yeah, so basically, yeah, the point is that the sample, any given sample is going to miss at least half of the points. So if you pick a function randomly, then on the missing half, we just have about half of a chance of getting it right. So if we take this expected value over picking the function f randomly, then for that we have this kind of 1/2 times 1/2 chance of or expected value of getting the wrong thing. So if we try to make this more precise, if we try to make this more precise, then we can say that this loss here, here we go. I'll write this out again. This loss df of so this is the average over C of this indicator function. So here for this average, we can actually we can underestimate this by restricting it to the sum being just over the points that are missed. So I'm going to write m, where m is the missed points. So these are, I guess one way to write it is that it's C minus the sample S bar. But I should say maybe, I guess minus the set of points SI in our sample. So yeah, if we sum over only the missed points, then we get an underestimate. And then we can say that this is also bigger or equal than 1/2 times the average over just the missed points. Right, just because the size of C is bigger or equal than 2 times the size of M. You're assuming at least half of the points are going to be missed. Does this make sense? So because we miss at least half of the points, the average over all of C can be banded below by 1/2 times the average over just the missed points.
So the sample S has size M, and C has size at least 2m. So
yeah, I should say.
yeah,
Yeah, thanks. Oh, wait. Oh, yeah, sorry. I sent it wrong. So we have the size of the sample is n. So that
Yeah.
means the number of missed points is
at least 2m minus at least m.
at least m, right? So I guess I mean that.
Yeah, okay, makes sense.
I mean this, yeah. Yeah, so I think I wrote the inequality the wrong way, but I did mean to.
I mean, I don't think that holds because like C has size at least 2m. So if you double the inequality on the left side,
we assume C
it
has
has exactly.
exactly 2m.
yeah.
Okay, so now this should be true. Okay, so and then the idea is that if we look at over a point that we missed, then when we take this average over all functions, we're going to have basically for half of the functions on a missed point, we'll get it right, and for half of them, we'll get it wrong. So the idea here is that if x is missed, then the kind of average over functions from C to Y of the indicator of alpha S of f being correct on that point x, or being incorrect, this is going to be actually exactly 1/2. Right, so it's exactly half of the functions that give you the same value as what was predicted by the learning algorithm. And one has to be a little careful here because the output of the learning algorithm depends on the function, but that's why we restricted the misspoints here, because if you modify the function on a misspoint, it doesn't affect the sample seen by the learning algorithm. So basically, to make this more formal, what you would say is that for any such point, you can like find a pair of functions which agree everywhere except on the point that was missed, on the point x. And then for that pair of functions, this indicator function have exactly opposite values. So the average of the two is going to be 1/2. So that would be the way to make it precise. But maybe for the sake of time, I won't write out that precise statement, but it is in the notes. Okay, so that basically finishes our proof, because we have this 1/2 here, and then this 1/2 here, and then we put it all together, you just get a 1/2 times 1/2, which gives us the 1/4 that we were looking for. So yeah, that's sort of the high level proof, and you can fill in the details either by looking at the notes or working it out precisely. Does this high level outline make sense? Or are there any questions? Yeah, so yeah, I think I actually quite like this proof. It involves a number of ideas. Basically a number of like moving between, like we show that there exists such a function by showing that on average something happens, and we kind of use this idea twice. And then it requires a bit of care with this last statement to make sure that we can actually say this. But hopefully on a high level, it makes sense that if the sample only sees half of our domain, then what happens on the other half is sort of in the dark. So for a random function, we get 1/2 chance of getting it right. Any questions about anything so far? Right. So basically, there's no free lunch theorem. I guess one bottom line of it is where is it? This corollary that we wrote here. That if we have an infinite domain, then if we take our hypothesis class to be as big as possible, namely all functions, then it cannot be pack learnable. And then, but we saw that hypothesis classes over an infinite domain, even if the class is infinite, it can still be pack learnable. So we basically tried to put this all together to an exact characterization of when a hypothesis class is pack learnable. So for that, we use this definition. That we saw that the kind of interesting thing was when we had a subset C on which the hypothesis class included all functions. So motivated by that, we can say that the hypothesis class H shatters a subset C if when restricting that hypothesis class to C, we get all functions on that subset, where this is just if you want to do this notation, a restriction of C onto C of H for the hypotheses in H. So this basically says that for this subset, when we restrict the hypothesis class, we get every possible classifier within that subset. Does this definition make sense? And then now we can define the VC dimension. So we say that the VC dimension of this hypothesis class is going to be the maximum size of a subset that's shattered by the hypothesis class. It's a maximum of size of C such that the subset C is shattered by H. And I guess this maximum might not exist, so we say that it's infinite if no maximum.
What does VC stand for?
So VC is the name of two people, which I tend to forget. It's like something Chernovsky.
Vapnik?
Yeah, Vatnik, Chernovsky.
Vapnik
If
or
you look
Vapnik?
at Vapnik, Chernovenkis,
Czerwonenkis.
Chervonenkis. Here I just shared it. Oh, there, someone already shared it. Yeah, I think these are two people who looked into this sort of problem initially.
So I'm curious, what is the significance of the VC dimension? I mean, I understand what it like means definitionally, but why do we care about it?
Yeah, so maybe I can just state this is sort of the fundamental theorem of statistical learning, which says that the following are equivalent. And as a shorthand, I just say H is PEC learnable if and only if the VC dimension is finite. And I guess you can say PEC learnable with realizability, or agnostically PEC learnable. So basically, the having finite dimension exactly characterizes PEC learnability for either realizable setting or agnostic setting.
So if
And then
so if the VC dimension is finite, then we don't need to assume realizability to know that this class is PEC learnable.
yes, it turns out something is agnostically PEC learnable if and only if it's realizability
Okay.
PEC learnable if and only if the VC dimension is finite. And in fact, this VC dimension asymptotically characterizes the sort of the sample complexity too. So there's a kind of quantitative version. We basically have if D is the VC dimension, and then we basically have the sample complexity of H for epsilon delta, and let's say let's say in the agnostic setting, this is basically it's equal to like theta of D plus, to remember what this is, log delta over epsilon square. Hopefully I get this right. So this basically says that there's a upper bound and a lower bound on the sample complexity that's governed by the dimension, and something like this. I wrote down the exact statements in the notes, but I think it's something like this.
Is there an intuition for why the VC dimension and pack learnability are basically like equivalent?
Yeah, so I mean, so the no free lunch theorem, it tells us that pack learnability implies finite VC dimension, right? Because in the no free lunch theorem, if the VC dimension is infinite, then we can apply the no free lunch theorem. And it tells us that it's not pack learnable. So basically the kind of this direction is the no free lunch theorem. And going backwards it requires more work. Yeah, we haven't proved that. Yeah, so going backwards it needs a bit more work, which I can say a bit more about what goes into the reverse direction. But maybe I answered half of your question, hopefully.
I guess the other direction involves finding a learning algorithm that works and then just doing the calculations. And
Well, yeah, so I guess so it turns out that something is pack learnable also if and only if, so I can just kind of include more things in the, if and only if the ERM, the expected risk minimizer, pack learns either realizably or agnostically. So basically it's enough to show that that one learning algorithm works. And then I guess there's another thing we can add to this list, which is that what we talked about at the end of last week, which is this uniform convergence property that the samples are likely to be representative of the loss. So there would be a kind of another item we can add to this long list of equivalent things, which is that H has uniform convergence property. So basically all of these things that we've talked about so far are all equivalent, which is it's a nice characterization, and it's all tied together by VC dimension, both qualitatively in terms of like learnability just means finite VC dimension, and also quantitatively where the various sample complexities are all very tightly related to the VC dimension.
So maybe this is jumping the gun for what we will discuss in the discussion group this week, but the thing we had in the homework, this hypothesis class that we were working with disks, that would have VC dimension 1, correct?
Right, that's correct.
And that's kind of that structure was crucial to being able to show that it's pack learnable, sort of.
Yeah. Right. So that family of circles, I mean, intuitively, it's a one-dimensional space of hypotheses. It has like a single parameter, and that's like an okay heuristic. Like you know, the VC dimension doesn't necessarily equal to the number of parameters, but on a very hand-wavy level, we can expect that that's sort of one parameter family of things to be one-dimensional. And in the last homework, you showed that in that specific case, it was indeed the case. Okay, and then maybe in the last few minutes, I'll just say something about what would go into the reverse direction, which is this very interesting result called Zauer's lemma. So it basically says, so we have that if we have infinite VC dimension, then if you restrict to a certain subset, then the number of the hypotheses in the restriction would grow exponentially with the size of the subset, right? So like maybe before getting into the lemma. Oops. So we have that y to the c, the size of this grows exponentially with the size of c. So in particular, you might just, if we have infinite VC dimension, then the size of this h sub c would also grow exponentially. So Zauer's lemma says that if the VC dimension is finite, then basically says that h of c, the size of the hypothesis restricted to c, grows only polynomially with a degree up to degree d, where d is the VC dimension. So this basically says less or equal to like O of the size of c times maybe something to the d. So it basically says that the size of these restricted hypothesis classes can only grow with a power d kind of into power of d instead of exponentially. And I guess there's a sort of more precise, specifically, we can actually show that this is less or equal to a certain sum of say it's like this. So it grows with this size of the subsets of C up to D. And then you can show that this actually gives you something of this form. Okay. So maybe I'll stop here. Are there any questions?
Have people tried estimating the VC dimension for realistic hypothesis class, whatever that might mean?
I think so. But yeah, I don't remember seeing such a result. That would be interesting to try to Google for to see what kind of like empirical results there or theoretical results. Like let's say like you have like a number of parameters for a neural network, which defines the hypothesis class. But what is the VC dimension of that? Yeah, I think it's definitely worth Googling for it.
So in this lemma, C is the
C is
C is the largest set that's shattered by H, or one of.
Well, okay, so this lemma is for any subset. So this basically is saying for any subset, the hypothesis restricted to that subset grows only as a power of D. And it's exactly because like basically up to the VC dimension, it grows exponentially because all of those are shattered. But then once you hit the VC dimension, any bigger subset is not shattered anymore. And this is sort of a stronger statement that says that in particular, the size of the hypothesis class only grows with the power of D. So this is it's a quite interesting non-trivial claim saying that not only is there not a shattered set above that dimension, it actually also bounds the size of the hypothesis when restricted to that subset.
Right. So like in the example we worked with, you could think of, okay, you take some set of points in R2. Using this hypothesis class we're working with, there's a very small number of ways that those points is basically for n points in general. There's just n ways that they could be separated according to the hypothesis class we were working with.
Well, so the VC dimension there is one, so that means that already there's a set of 2 points which are not shattered by a subset. Namely, if you take 2 points in a single circle, those are either included or not. So those are not shattered.
But let's say you take 10 points. There are basically, okay, there are 11 ways that you can label 10 points because you're always going to label them starting with the point that's closest to the origin.
Right.
So there's basically this D is 1, right? As the number of points increases, the number of possible labelings of the points just increases linearly.
Right.
Very cool.
Yes, it's interesting to note here that if the size of C is less or equal to D, then here we're summing all the way up to any subset. So here, in that case, we just get 2 to the C. So it is exponential up to the VC dimension. But then, yeah, once you hit the VC dimension, then afterwards it's just it's governed by this exponent.
Can you say something about why SLT is useful in the alignment world? So, I mean, I have a vague intuition for like, okay, agents, it's worth understanding the theoretical foundations of agents. Why is it useful to learn about supervised learning as well?
Right. I mean, for one, they're like reinforcement learning and supervised learning are pretty closely related. I guess we saw a lot of the theory looks quite similar, and in fact, yeah, it's interesting to ask like what would be the analog of the VC dimension for an RL agent. But yeah, I would say that maybe supervised learning is usually like a little easier to understand than reinforcement learning. So it's a good sort of it's a good ground for developing some of the theory of learning in general. Yeah, so a lot of the, I think a lot of the things that can be understood from the theory of supervised learning, you can ask, okay, how can we carry this over to reinforcement learning? So in that way, it's useful as well. And you know, I mean, a lot of the machine learning today is still some form of supervised learning, be it like image recognition or something. So I think it's still a kind of a practical thing to try to understand the theory of supervised learning as well. But yeah, maybe if you only care about like agents and reinforcement learning, then you can treat supervised learning as sort of a toy setting. But you know, it's already fairly complex, so maybe unfair to call it a toy setting. But it's usually a little more contained, like easier to understand than RL.
And like, what kind of result in SLT would help us understand like empirical deep learning? So this stuff about no free lunch theorem, I don't see how it applies in practice because, well, we make strong assumptions on what hypotheses we consider.
Right. So I think that is still like an interesting question to understand, which I think we talked about last week a bit in the discussion. You know, there's this phenomenon of like overfitting, and there's this sort of classical understanding of overfitting being bad, and then how it tends to look different in deep learning. There's this like phenomenon of deep double descent, where at some point, if you overfit enough, you get something pretty good again. And I guess that gets into the other SLT, which is a singular learning theory of trying to understand what kind of priors do deep neural networks have that make them still good learners in the sort of overparameterized setting. So yeah, I guess that sort of question leads into maybe the theory of deep learning itself, which is what's being developed under singular learning theory.
Yep, thanks very much.
Yeah, but then I guess so I would say like singular learning theory is a sort of vein of research which is closest to practice, like or having to do with deep learning. But then you can also kind of take a step back of like looking at the more abstract level of, you know, there's this distinction between the realizable setting and the non-realizable setting. which already shows up in supervised learning, as you saw. And I guess based on this theorem, we saw that learnability actually turns out to be the same for realizability and non-realizability for supervised learning, although they have different sample complexity. In the realizable setting, we actually only have a over epsilon here, so the agnostic setting is still arguably harder. But then I think for reinforcement learning, maybe it's more interesting, especially if you consider embedded agency or multi-agent scenarios. Then in those cases, you're basically always operating in the non-realizable setting where like an embedded agent or kind of or in a multi-agent scenario, you cannot expect to have a fully accurate hypothesis, because I guess because of some like impossibility results of like Gödel's incompleteness or halting problem, where like an agent cannot describe itself fully, or even another equally complex agent. So there you're always operating under non-realizability. And then so there is an interesting question of what it implies for an agent to not have this realizability. So that would be something that's a question. It's a more abstract question of like, it doesn't even involve neural networks. It's just asking what does a good reinforcement learner look like, which doesn't assume realizability. And that already like applies on the level of ICSI, for example, because ICSI has a hypothesis class of computable environments, but ICSI itself is not computable exactly because of this impossibility result. So like ICSI is not capable of describing itself as being part of the environment because all of its hypotheses are computable, but itself is not computable. So that would be a more theoretical obstacle, which is a interesting research area to try to address. I think I mentioned this before, that you can basically take any assumption that we made so far and ask, oh, what if we remove that assumption? And basically, like, I think basically, yeah, any of them you pick out, you're going to end up with like a new research project that can be quite hard and interesting. And maybe I mentioned this before. The one thing I've been looking into is, one of the assumptions we made is that, for example, in reinforcement learning, we made the assumption that we observe the reward. What if we remove that assumption? What if the reward is something not observable? Which I think is like realistically, you might value things that you don't observe. And you can ask, okay, well, what kind of hypothesis classes are still learnable under this when we remove this assumption of observing the reward directly? And yeah, that turns out to be a pretty complex research area already.
What do we replace it by if we don't have reward? Because we still need, some direction for the agent.
Right. So yeah, there's sort of two approaches which turn out to be equivalent in that case. One is you can still like posit a set of states, like states of the world, which are not directly observed, but maybe partially observed. And that you can assume that your reward function depends on the state, but not on the observation directly. So that's one way to formulate it, which would be you can call it hidden rewards, and that's yeah, that's a very simple setting, which is it seems to be not well researched as of now. And then another way to say it is that okay, you don't observe the rewards, but maybe you can find out about the reward if you wanted to. Like let's say I'm trying to decide between a silly example or a more serious example. I think maybe like let's say you care about the suffering of people in Africa, but you're definitely most of the time not observing that in any way. But if you wanted to, you could travel to Africa and see and ask the people how they're doing. So it's possible to find out if you wanted to, but it requires a specific sequence of actions to find out about something that you care about. So that would be another way of saying that it's possible to perform an experiment which gives you some indication of something that you care about. And that's an interesting result already. That it turns out that these two formulations are equivalent. Like in both of the cases, you can set up an equivalence between having a hidden reward, which depends on some state of the environment, or having a kind of reward that depends on a certain experiment you can perform that tells you about what the reward is. All right. If there are no other questions, maybe we can stop here and we can have a discussion on Friday.